Ladies and gentlemen, welcome to the second day of our virtual summit. Today, we will delve in a range of thought-provoking topics that shine a light on the complexities of our digital world. We will start today examining architectural choices and why they matter. Then, we will move on to correction methods that are resistant to attacks because resilience has to be in the nature of any organic system. Digital integrity rights will be explored, focusing on the right to privacy and the right to be free from surveillance. We'll also delve into artist right management in the Web3 era, aiming to empower creators and ensure that they have control over their work. We'll continue with the potential of decentralized artificial intelligence, hot topic these days. Additionally, we will explore the state of the art of the promises and execution of games on the blockchain. Prepare to be intrigued as we explore the concept of NFTs you can eat. A fascinating intersection of art and gastronomy that challenges our notions of digital value. Tools to resist censorship will be presented, equipping individuals and communities with strategies to guard free expression and access to information. And lastly, we will examine how blockchain technology can be harnessed by activists to fight for justice and equality. Join us on this journey as we examine this technological landscape and explore ways to shape a more resilient digital future. Welcome to the second day of our virtual summit. So, let's begin. The flapping of the wings of a butterfly can be felt on the other side of the world. Have you ever wondered what is the difference between IPFS and Swarm? The next talk is about how subtle, low-level architectural differences can play a significant distinction in how data is stored, private, and incentivized. Why all this matters when it comes to requirements like data availability for rollups. Why the vision of the Ethereum founding fathers for the evolution of the internet that they called the world computer needs, begs, cries for a system like Swarm. It is my honor to present Victor Tron, team lead of Swarm.
Hello everyone. Using an old tagline, the word computer, we're going to introduce Swarm in this generic context of serving as a data layer for this word computer. So what is the word computer? It's meant to be the base layer infrastructure underpinning the newly decentralized World Wide Web, an operating system for web applications. When the founders of Ethereum first formulated the idea of a Turing-complete blockchain, they recognized it as a global consensus layer for secure computation. They started imagining what a complete computation environment would look like. This blockchain can be implemented to give a full infrastructure. Components of this infrastructure were conceptualized using an analogy of computer hardware. The Ethereum blockchain being the CPU of this computer, they envisioned hard disk of data storage called Swarm and a messaging layer called Whisper, referring to these as the Holy Trinity. It's somewhat of a gimmick. Since then, a lot changed in the agenda of the Ethereum space, but Swarm carried on with the task of defining the components that are needed to complement the blockchain and make the word computer a reality. On the one hand, this context will shed light on why Swarm is and should be a one-stop stop for all things data storage and transfer, namely how come Swarm is ambition to satisfy all the contradicting requirements, seemingly very different use cases, ranging from serving, hosting apps, real-time interactive web applications, all the way to the static storage of backup data of personal collection. On the other hand, you will learn in what ways Swarm is different from many Web3 projects, the sister projects, and in particular, you will learn to appreciate why low-level architecture choices matter and how they determine the important features required of such a generic data layer. Now, what is the evaluation criteria? We classify them into three major groups. One is to do with representation, basically how data stored in the network is chunked to smaller units and how these units form a higher level structure, basically how they include structures that are semantically meaningful and relevant to the users, namely files and directories, and in general about internal and external relationships between these blobs of data. Second area is persistence, which is concerned with how long and how certain we are that we can access the data. I choose to call these persistence guarantees, and it concerns with ways of assuring data availability or give persistence guarantees, namely including redundancy, stewardship, and economic incentives. The third aspect is what I call privacy, and relates to permissions, who can access the data and who knows who can access the data. This is more familiar terms concerned with encryption, access control, plausible deniability, and censorship resistance. Just to illustrate the complexity of requirements imposed on a generic data layer, let's see a very simple use case: hosting a decentralized application code. This raises various concerns about the usability. First of all, it requires some URL-based addressing, which people are used to when using web applications. This can be described as a mnemonic reference to a collection that change, in particular, over time as you have versions or update of your site. And it has a path-based reference to an asset within this collection. The former already requires mutability and can be solved by the Ethereum name system and it's a service on the blockchain. And this ultimately anchors the data to the consensus layer, which is very important, but it provides mutability that has high transaction cost and relatively infrequent updates made possible. The latter, so path resolution, needs representations of a collection and basically lookup mechanism to look up the particular path and what asset it belongs to, the asset it points to in an index. Importantly, application hosting already raises a privacy requirement, and ideally accessing a Web3 that should not leak user's identity, therefore requiring the requester's anonymity. Also, in the spirit of true permissionlessness, making available a Web3 user interface or the app must not be subject to the whims of gatekeepers, and in general what we can call display censorship resistance. Also, serverless data support include searchable structured data and necessitating the update of databases with a much higher frequency than the on-chain Ethereum name system can solve, and also should ideally provide update patterns, so representations where updates optimize. So when you insert a new item in a database, then you should be able to get away with the least amount of new blobs that you create. It also should solve historical persistence, and basically being able to find a historical state or different earlier versions, same database with the same solution, and it should provide for infinite scalability of the amount of data. In order to understand better the low-level architectural choices that make Swarm different, we turn to listing some commonalities between currently active contenders to the Web3 data layer race. And out of these commonalities, we focus on the areas where there's differences between them, in particular where Swarm makes a different choice. Most of these frameworks imagine the underlying infrastructure to implement the decentralized storage as appears to be a network of nodes that use some kind of direct underlying transport protocol, namely, for example, TCP/IP or WebSockets. And this is augmented with an overlay connectivity pattern. So basically, the topology, if you want, describes how peers can connect with each other. The overlay address space can define routing protocol within, ultimately to allow any part of the network, any node, to reach any other node in another part of the network. And in particular, this overlay connectivity, which states that nodes address themselves, these approaches usually use content addresses of the pieces of data that is stored in the network. And the address means that the address reference to a piece of data only depends on its content and not on its origin or what the structure is a part of. Since content address is changing, if the underlying content changes, it's an immutable link, and therefore it provides an integrity solution to content. integrity verification for the content. And it's usually combined with the model where we place the nodes in the same address space in the overlay topology as the content address of chunks. So although this is a common practice in these systems, these peer-to-peer networks, one difference lies in on the one hand in their storage model, basically where the actual data is stored, and the second is how this routing is implemented. So for the storage model first, we can simply call the two types of approaches. One is for file sharing paradigm, the other one proximity or address-based storage. In the case of the file sharing paradigm, you say that nodes participating in the network just open up their hard drive and get their content registered in a distributed index, but the index actually only stores the information about where the chunk can be downloaded from. And as opposed to this contrast, in the file sharing paradigm, the address-based storage model achieves storage of content, requiring that nodes that are proximity of the content address have this chunk in the area of responsibility. So they basically store the content in the neighborhood. This storage model is very different from the argue that it's superior in terms of the features that it allows. Now, as for incentives, it's important that most earlier solutions to the decentralized and distributed storage hosting used similar network protocols and similar architecture, but most importantly, they lack incentives. Since peer-to-peer networks are not operated by some entity with external liability, reputation, or legally enforceable obligations, the resilience of this network needs to be underpinned by incentives. So, in other words, the nodes need to be motivated to do what the protocol prescribes them to do. Modeling nodes as operated by rational profit-maximizing agents allows for monetary incentives to be supplied, and these should drive the protocols and make the network economically self-sustaining. The strongest interpretation of such an incentive-based network would claim that no strategic behavior of any peer should be left to chance, and instead every strategic move that the protocol prescribes them to do is incentivized by some economic rationale. Therefore, the outward behavior of the network serving rationalities that cloud service such a network should do on the level of nodes translate to rational profit maximizing. And this is why Swarm is called Swarm, because the behavior of the colony of bees is different from the individual bees motives. And then the network's behavior to serve as a cloud service emerges from the individual node's behavior. Let's investigate again the stewardship-based approach to file origination. In the file sharing paradigm, basically a publisher is the one responsible for storing originally the content, and then it opens it up for download, and the replication of this content done indirectly by the consumers when and where they retrieve the content, and also possibly the insurance or assurance that this content is available is after all the client's live and online, then as long as there's true that the content is available, they go offline, they assign this responsibility to their consumers. So it's not ideal from the outset for content that is not supposed to be replicated, like backup data. First storage, as opposed to this address-based storage, means that chunks are stored with nodes whose overlay address is close to the content address of data. This implies right from the start that there needs to be a protocol which makes sure that when content is uploaded, that the chunks constituting this content to the neighborhood that they belong. Such a protocol already has a few benefits. First of all, it shows that the solution is a proper cloud service. So because the content is not preserved on your hard drive and just opened up to the public, it's actually properly uploaded to the network. It's transferred to the neighborhoods where they belong. Therefore, users can just have a behavior which is called upload and disappear. So they can use a cloud service and they not necessarily need to have even a storage on their own. Imagine just a mobile device with no storage, just streaming video directly to the network and it's chunked up into smaller pieces and these are transferred to the neighborhood. This protocol that distributes the content to the destination provides for the possibility that the neighborhoods synchronize the content And so there's some local redundancy right away from the outset. This already gives some resilience against node shard or accidental outage of particular nodes, and still allows successful routing for retrieval of the content. It has the added advantage that it does not leak anything about the originator of the content, because the content is not downloaded from them, but from wherever it lands in the network. It also does not leak what chunks belong together from the file, because they encrypted and chunks are scattered around in the network. There's no way to pin them together and have any clue about what chunks belong together to form a bigger structure. Incidentally, and most interestingly, the third benefit is that this upload protocol provides cover traffic for messages, which is considered a unique feature, which we discussed at the end of this talk. We mentioned that peer-to-peer networks use an underlay transport protocol, such as TCP/IP, and an overlay topology for routing. If one chooses a keep-alive connection in the underlay connectivity, and therefore have a quasi-permanent set of peers that a node is connected to, this solution has the immediate benefit that you don't need to establish a new secure channel network protocol for every request to peers. And also you can be sure which of your peers are online and available, because those that remain connected to the keep-alive connection are ones that you can communicate to right away. This enables request forwarding, the type of routing that is in contrast with iterative routing. Iterative routing is analogous to when you ask your friends to give you someone who you think might know a person that you're not connected to in your network, and you iteratively get closer and closer leads to this unknown address. And ultimately, you zoom in, and in the spirit of full connectivity, you zoom into the person that find you who you were looking for, and get their contact, so to say, but you ultimately contact them through an iterative process. As opposed to this, message forwarding has the immediate benefit. The originator remain ambiguous, because as opposed to the iterative method, it works by outsourcing the request to a peer that's closer to the destination address. So basically, it goes through the request is relayed through a number of forwarder nodes, which are in ever increasing proximity to the ultimate address, that is the destination of the request. And the response, which in case of a retrieval request is a chunk, with its data, this response is passed back along the same route as the request was forwarded on. And therefore, because it's passed back through nodes that did not request it, they offer the chance for these forwarders to opportunistically cache the chunks if they want to store them. And this is the most beneficial, profitable way of doing this, is to keep caching stuff and ultimately keep the ones that are often requested, and this because that will increase the bandwidth reward that you get for serving the content. And this implements basically auto-scaling of popular content. So popular content which is requested are simply dispersed and distributed within a wider set of nodes, therefore increasing its availability and decreasing the latency of retrieval. So surprisingly, the live connections and forwarding enable scalable microsystem payment system. As we mentioned, when you request, you used to forward your request to another peer, you basically incur a bandwidth accounting event. You basically account for what bandwidth resources were used in your interest. So when your request is forwarded, then you get debited, and the other peer gets credited for this bandwidth sharing resource distribution. And as the accounting allows for certain tolerance of unequal consumption, after a while, the tally tilts, and the one peer gets potentially indebted gets to be in debt of a certain threshold, which necessitates the settlement of debt. And the settlement can be done micropayment settlement solution, which having settlement arrangements with your peer based on the pattern of repeated dealings, which means that this accounting and the tietted debt it only makes sense if you often interact with this peer. This is exactly what forwarding allows you to do, because just imagine that you have a request response interaction with the ad hoc peer one-off. In that case, you don't engage in a bandwidth that peer, but the bandwidth accounting goes to the sequence of forwarding nodes, and therefore also is seen on the same peers that you can connect it. Overall, this pattern allows for a logarithmic number of peers to have higher payment arrangements with, and that fires very well in the number of nodes. So if the network size is big, the number of arrangements that to be maintained is just logarithmic. Going beyond the bandwidth incentives, we also, as we said, in a strong interpretation of an incentive-based solution, is that contributed resources should be motivated and should be motivated with economic incentives. Positive incentives mean that means that nodes storing the content get rewarded upon showing evidence of storing the right relevant content in its full integrity, but no punitive measure is implied if any particular piece of content gets lost. This contrasts with negative incentives, which is essentially insurance, and an insurance sign up for the collection, they are third party revered, and the collection is also known. So those systems which the storage incentives are in the form of a marketplace or providers, with the collection and the originator a unique identity, and therefore provide an attack surface and raises privacy concerns. As opposed to this, the argument for a solution where the primary incentive system is positive incentives, and therefore we can maintain on this non-leaking privacy conscious solution. Redundancy is another area which can be said to be responsible for data availability. It can be interpreted as the degree of replication, and you have local redundancy, local replication of content in neighborhoods. This is resilient against node churn and the accidental offline of nodes. When you have non-local replication, we also mentioned this before, you have a cache of the popular content is cached by nodes outside their area of responsibility. But most efficiently, redundancy can serve data availability through a pattern called erasure coding. And erasure coding is a solution where a number of chunks or blobs of data is inflated to a bigger amount of data, and chunks get inflated into n plus k chunks in a way that out of these n plus k chunks, any n chunks found can reconstruct the original content. This gives for a very flexible storage pattern because it allows for many different ways to reconstruct the content, and it cross neighborhood redundancy. Doing this way, you can protect against the very unlikely or the more damaging scenario of whole neighborhoods being unavailable. This can be due to gaps in your node's peer table, due to topology error, and it can be also a result of actual targeted text against the neighborhood, or just in general an unlikely constellation of network contention and unavailability of nodes due to network error. Importantly, this erasure coding scheme is user configurable, so it can be configured to represent your risk and security requirement against any amount of network error, all the way to potential protection against network split. Now let's turn to different realms, basically the realm of communication. So we mentioned the storage model and the routing model to be distinct low-level architectural choices that have far-reaching consequences in terms of what features the network can realize. But we must not stop here. If we want generic data layer to power Web3 with a serverless setting, we not only concern ourselves with how data is stored, but also how it's distributed, transferred, queried, and discovered. If we go the whole way, and then envision that to implement the serverless internet, it take care of functionalities that in Web3 are typically, in Web2 are typically carried out by server-hosted databases, server-side processes, and server-mediated communication and notification subsystems. This latter one is maybe an important one to mention, basically server-mediated communication and notification subsystems. So there are two communication primitives in Swarm that together very powerful and really specific innovations of Swarm, and they allow for the entire spectrum of communication modalities to be modeled with these primitives. First of all, the first one is due to the construct called single owner chunks. This type of chunk wraps the content address chunk and attaches to the data an attestation associating the content with an ID, with an arbitrary ID. Such an attestation is basically a signature given by a signer, and this signature gives the chunk's integrity, and it's verifiable locally by any forward node. This attestation licenses the chunks to be under an address which is derived from the ID and the Ethereum address of the signer. This might sound complicated, but in simpler terms, it means that single owner chunks virtually allocate a private namespace to any account, and the owners of this account are allowed to determine what content is associated with an ID. So if the ID itself follows a semantic convention and the owner address is known, this construct can be seen as advertising content under tags which are discoverable by the readers. So, in other words, if the ID indicates something like content, comments to a particular post, then looking up the comments of this particular post only requires this ID to be hashed with the inquired, and that's how you can discover whether your friend left a comment to your post. And the same can also implement things like what you see in Web2, like the Facebook likes of your friends on a particular page, but this can be done without inserting anything in the original post. It can just be overlaid on the solution. If the ID is specifically construed as a combination of topic and a sequential index of some sort, then single owner chunks can implement feeds. Feeds can represent a great variety of things, among others. They can track versions of an asset. They can represent status updates. They allow representation of mutable content and with any frequency that is higher than what the Ethereum name service on the blockchain can allow. Most importantly, these feeds can implement communication outbox, which, if mutually agreed on by several parties, can implement a multi-party chat, which can also be completely dark and inaccessible or even undiscoverable by others. Since feeds are poor media, which means that the recipients of this outbox messaging needs to poll the relevant outbox address, then this makes it inefficient for updates, which are sporadic. For example, blog posts that you sometimes update every day, but sometimes you wait 2 months to write the next one. So this is inappropriate for polling, and for these, especially, you need potentially some notifications and then new content arrives, and when an already known chat partner starts a new chat. This requires the other primitive, which is called node addressed messaging. Node addressed messaging means that the messages to recipient are pushed to the node representing the recipient, and the message then can take the form of an uploaded chunk. In fact, you can send the message as a Trojan chunk, which means that a chunk that is to any third party indistinguishable from a normal encrypted chunk, but can only be opened by the intended recipient. This way, the recipient can remain completely hidden, and it allows for anonymous senders. They are produced by mining the resulting content address chunk into the proximity of the recipient address, the overlay address. This mining or this process of finding a non-semantic part of the content address, which makes the hash of the entire message in the proximity of the recipient. This is a costly process. We are talking about max a second delay, but still it's not appropriate for frequent exchange of messages or real-time data exchange. And this is only used for the purpose of establishing contact. So basically it's used as a handshake. But advantages, namely this allows for asynchronous message delivery. So the recipient does not need to be online at the time of sending the message, and they can, at any later point in time, can pick up the message by simply synchronizing the content with their neighborhood. They don't even need to be a node that's long-term online in that neighborhood. It can be just a network that's created. It also inherits incentivization from generic chunk storage and upload. Since the generic uploads and the flow of uploaded chunks, the upload protocol provides a much needed cover traffic for these messages. This makes them ultimately resilient to traffic analysis attacks. So that's why it's justified to call them this primitive zero-leak messaging. So zero-leak once again, it means that besides confidentiality, which is easily achieved by end-to-end encryption these days, very common in messaging solutions, it also provides anonymity of sender and recipient. And what's more, but most importantly, it provides less messaging, which means that the effect of message sent is also left undetectable. This is quite a strong proposal, value proposition, and I know of no communication system that can provide this level of privacy. To conclude, I hope I convinced you that Swarm can serve as the generic data layer for Web3 due to its rich feature set. Most of these high-level features are made possible indirectly through low-level architectural choices, which I hope I convincingly argued not insignificant implementation of details, but actually matter a lot. These included ways of doing storage, the ways of approaching routing, the primary choice of incentives, and a few more primitives and